Okay, I've started drawing the diagram for problem 3 already. It's got a trampoline, so there's a little trampoline there. And the trampoline behaves like a Hooke's law spring with a spring constant of K equals 500 newtons per meter. There's a boy who is bouncing on the trampoline. When he goes up in the air, he goes up to a height of h above the neutral position of the trampoline. And I think I forget what I said h was. Oh, h is what we had to find. And when he compresses it, or when he's in the trampoline, he pushes it down by a distance, I'm going to call it x, but I think I said x was 0.75 meters. The spring constant for the trampoline is given by K of 5,000 Newton meters, and sorry, I guess that looks kind of, or newtons per meter. I guess that's kind of ugly looking. Maybe it's a little better. Okay, anyway. And the boy has a mass of 30 kilograms. So we want to find out the height h the boy bounces up to, right? So what I'm going to do quite simply is I'm going to take two states here. So let me identify them and label them as usual. There's state 1 and there is state 2. At state 1, we want to find the boy's kinetic energy, his potential energy due to gravity, and his potential energy due to the spring. And then at state 2, we want to find the boy's kinetic energy, his potential energy due to gravity, and his potential energy due to the spring. Okay, so let's start with stage 2 just because it's there. We're talking about the highest point the boy reaches. So at the highest point of his jump, he's momentarily, not moving, or he momentarily has a velocity of 0. So at that point, his kinetic energy is 0. Potential energy from gravity, that's given by m times g times h, right? So that's just going to be mgh. And then the spring potential energy, well, at this point, he's not even touching the spring. So there's no potential energy in the spring. It's completely uncompressed, so it's 0. Okay? Now, point 1, this is where he's at the very bottom. He's just pushed it all the way down as far as it's going to go, and now he's about to spring back up. So there, kinetic energy is also 0, because now he's frozen for a minute. Okay? Gravitational potential energy is going to be... Now, this is where it gets tricky. We said right here, this line here is where gravitational potential energy equals 0. Right at this point, that's what we said, because to say that gravitational potential energy at 2 is mgh, we're then implying that gravitational potential energy here is 0, which means gravitational potential energy at the bottom is not 0. It's actually negative mgx. Okay? And then the spring potential energy here is at its maximum, which is 1/2 kx squared. So it's compressed by x. So let's find the mechanical energy at both points. Mechanical energy here, at the very bottom of the spring, is this negative mgx for gravitational potential energy, plus the 1/2 kx squared for spring potential energy. Okay, let me just draw a dotted line through here. And then on this side, E mech is going to equal 0 kinetic energy, 0 spring potential energy, just the mgh. Okay, if we set these two equal now, so we neglect non-conservative forces, and we're just going to say negative mgx plus 1/2 kx squared equals mgh. And what that ends up doing for us, I'm going to bring this side over, okay? So now we're going to have 1/2 kx squared equals mg times h plus x. Okay, and let's see, what else can I do? I can divide both sides by mg. I'm solving for h here. So thankfully that's a lot easier than solving for x. There's no quadratic. It's solve for h in terms of, we already have x, so solve for h. So what I'm going to say is kx squared over 2mg equals h plus x, which means then, finally, drum roll please, h equals kx squared over 2mg minus x. There we go. So now, let's see where this puts us. X we said was 0.75, so, and k was 500. Let's say 500 times 0.75 squared divided by 2 times mass of the boy times 30 times, I'm going to say 10 for that, and then minus 0.75. And so the answer should be, good lord, is that correct? If that's correct, then I have completely screwed up. Interesting. So this means the boy actually does not even get all the way up. That is kind of pathetic. Let's see. 0.75 times 500. 0.75. So, boys. That seems kind of strange to me. It doesn't make it all the way up, but maybe I've really screwed this one up. So, 500 times, let's make sure I got this right, times, and divide it by 2 times m times g minus 0.75 is, yep, there it is. Well, son of a gun. So I guess with the numbers I made, the boy just cannot even get up off the spring. He's going to sit there and sort of pathetically bounce up and down, and he's going to say, "Oh, Mom, Dad, why did Dr. Smith make this trampoline so shitty? I can't even, I'm sorry, so crappy. I can't even get up off it. Oh, well, this is horrible." Okay, so the moral of the story is I guess he needs a tighter tension as trampoline. Like if, say, K was like 4 times as much. So I'm going to do this in purple. I'm going to say if K was equal to 2,000, let's say, newtons per meter, then it would actually be something more like so then you get like a meter, a little over a meter up, which is at least something. That's a little less pathetic than the one I have there. So, moral of the story is if you want your trampoline to bounce you a decent height at all, make sure it's reasonably tight, because a saggy trampoline with a low spring constant doesn't get you anything.